In hitting upon the formulation, I think, therefore I am, Descartes took himself to have established not only his existence, but his nature. He is essentially a thing that thinks. Thought, that is to say, is the essence of mind. There are two aspects of thought, that are of particular philosophical interest. Its representation of things beyond itself, and its movement from one representation to another in accordance with the laws of logic. The laws of logic. That's what we're studying in this class, the laws of logic. The movement of information represented inside our minds from one equation to another, from one state to another. The other aspect of thought is representation, knowledge representation. How do we take things and represent them? That's the study of artificial intelligence, which is another course. If we want to build machines that reason, we need both of these things. We need to understand how to represent the knowledge, and then how to calculate, how to go from one true statement to another according to some reasonable set of rules. And that's where logical reasoning comes in. So that's where we're at as computer scientists. In this video, I'm going to go through 3 proofs showing the conditional proof rule and introduce a new concept for proofs called the subproof. So let's get to it. Here's a standard thing that we've been doing over and over again. We want to show that this is a tautology. We start off with the premise, but then we do a new thing. Like, what we want to show here is that an implication is true. That this implication itself is true. But over here is another implication. The consequent is another implication. So to show this consequent is true, right? We start off with the left side over here. And now we want to show that this consequent is true. And so what we do is we introduce a new premise to the system. If I want to show if not B, then A, if I were writing this out in English, I would write something like, okay, well, let's assume that not B is true. And then you have a chain of reasoning that concludes A. And so then you say, okay, so I know now if not B is true, then A is true. We don't have words to that effect in our formal logic. So instead we rely on indentation. We have to indent the subproofs. And then we introduce a new premise. And in parentheses here, we put that it is for this particular implication. This is not a premise for the entire proof. This is a premise for a particular subproof. This is, suppose that not B is true. Let's see what that gives us. We've introduced a new premise to our system here. I can now apply these other rules. So now I can look at 1 and 2 and use disjunctive syllogism to conclude A. Which is what I wanted. It's not hard proof, it's just a new thing. And so then I come back out and I use my conditional proof rule. I say now, because of what I did on 2 and 3, I can conclude that not B implies A. And this is how we interpret this derive over here in the CP rule. We see that we start with the not B. We have a chain of reasoning that gets us to the consequent. We've derived B from this, and then we can conclude the implication is true. The implication being true is back out unindented a level. So that everything indented here is called a subproof. And when we finish the subproof and make our conclusion using CP here, we now discharge these premises. They become discharged, which means that later on in my main proof, I cannot access them. These lines here now, lines 2 and 3, are off limits for the rest of my proof. They were only for this subproof. That makes sense, right? You can't just introduce a premise and then use it forever, right? I'm introducing this premise for the express purpose of proving that this implication is true. Once I've proven the implication is true, that is all I can conclude now. I can't now just keep using the not B being true. Otherwise, you could just keep introducing premises and then the whole system falls apart. All right. Now we're done, right? So now I've shown that A or B being true gives me the consequent over here. And again, I apply CP again, because this whole thing now is also an implication. We've got two levels of implication that we're trying to prove here. And this also maybe shows you why, when we use the conditional proof for the whole thing, we don't number the line. Because in effect, we're unindenting yet another level, where we're coming out a level. This whole thing is basically a subproof, and we pull out of it to conclude that the implication is true with the conditional proof rule. So just like here inside this subproof, we've gone back a level of indentation to conclude not B implies A is true using CP. We do the same thing for the entire proof on this last line with CP here. So whenever we conclude an implication is true with conditional proof, we always go back a level of indentation. There's a bigger one. Let's try this. We've got another big implication here to prove, tautological. This time we're going to have to do two subproofs, because we have implication here and implication here. So our strategy here now is to show that both of these things are true. And you should start being able to kind of look at this, plot out a plan of attack, and start thinking about which proof rules are going to come in use here. Like when you sit down with the programming problem, you don't just necessarily start blindly throwing statements together. You think out what sort of statements am I going to need, what sort of algorithm is this going to be. So the same thing can apply here once you get some more experience with this. And there's a lot of examples in the text. This textbook is fantastic with examples. Read through the examples, make sure you can follow them. There's a bunch of problems too that you can work in the text in addition to the assigned problems. So now what I do is I build up A or B with addition. I can use modus ponens now. So the opposite isn't a problem. If I'm in a subproof, I can access lines outside of that subproof. I can access main proof lines inside the subproof, but I can't go the opposite way. I can't go back into the subproof once I have discharged those premises. So here I'm using modus ponens with 1 and 3. So 3 is inside my subproof, 1 was in my main proof, but that's okay because I'm in the subproof. And then I come back out. And so now I have A implies C is true because of this derivation in here. So when we write from A derive B, that's what we're talking about, this derivation coming down here. Now I have to do it again. I got to do it again for B implies C. It's the same sequence of statements, the exact same form of the argument here to get this other side. And then I combine them with conjunction. We're done. Notice the numbers here for CP. This is a little different. I can't access lines 2, 3, 4 and lines 6, 7, 8 inside to call CP here. I don't have access to those. The only lines available for my main proof are 1, 5, 9, and 10. So those are the ones I call on. I start on this and I derive the consequent. From A derive B. That's what I've done. From the antecedent up here, derive the consequent, which is this. So then I can come back out a step and conclude CP. But what steps of this are in my derivation? It's only the steps that are unindented. It's only the steps that are part of the main proof, not the steps that are part of the subproof. It's just make sure you understand how that goes. Think about writing this out in paragraphs. Think about doing the informal proof of this. You would say, okay, we're going to assume A, and you're kind of wrap this up in a lemma. And you'd wrap this up in a lemma, and then your main proof is, oh, I've got this as a premise, this is my given, and then I've got these two lemmas, so then I can just kind of write some informal sentence to represent conjunction, and you're done. Okay, here's the last one. We're just going to look at this here, and we have this many implications here. So I just wanted to show here, it's all right here, so you can see the full proof and what it looks like. And we have a subproof inside a subproof for this. So we've got this implication here, but then I have to do the A implies C also inside of here. So we're doing this, and then this one has a lot of arrows in it. So spend some time looking over this. We start off with the given over here on the left. Then I'm going to assume the A implies B is true because I want to show this whole implication, the entire consequent is true. But then I have to assume A is true so I can show the consequent of this inner implication is true. I use a modus ponens all over the place, and I pull back to get A implies C is true. So this, every time you come back out, you have to correspond the conclusion here with a use of CP with a premise that you've introduced to the system that specifically calls out that implication as what you are going after, as what your goal was. And then here I've introduced a new premise for this whole consequent over here, so I pull that back out. So now this A implies B gave me this line, and then I'm done with the whole thing. 3 CPs here in a row. Again, the only lines of the proof that I have access to for my main conditional proof, for my main theorem, are 1 and 8, because everything else is inside subproofs. And for the first subproof, it's similar. Here I only have 2 and 7 to work with. I don't have this subproof here, this inner subproof 3 to 6. That was taken care of. It was a subproof of a subproof, but that's fine. We're used to thinking in abstract hierarchical terms in this business of computer science. So there we go. This is really important, because what we want is to be able to represent thought inside our computers, and we want to be able to run through thought. So this both gives us a understanding of how to formalize something so that we can automate it, and it also just builds up our own abstract thinking abilities and works to further our own intellectual development. And that's really why we're here.